We learned how to write chemical sentences last time and how to balance the equations. And I think that's about as far as we got. Oh, stoichiometry. Yeah. We did stoichiometry with masses. Okay. Today, we're going to look at different types of chemical reactions first. And I think probably next Tuesday, we'll look at stoichiometry of solutions. But just as a heads up, solution stoichiometry is essentially the same as what we've done so far, except you convert to moles, not by molar mass, but by units of concentration. So you end up in the same place. It's just that you have to use a different method. All right, so let's get rolling here. You ever heard the expression, water is the universal solvent? Yeah, it's not really, but it does dissolve a lot of things. Some things it dissolves very efficiently. You can put a lot of stuff into a solution, and other things you can only put a little bit. But since, who is that? Since we're essentially big bags of muddy water, and biochemistry is most often associated with water as the solvent, then we're just going to focus on water as our solvent. Water has a special characteristic, and we'll get into, actually the second semester is when we really get into the weeds with atomic structure, I think. No, we do it at the end of this semester. Good, you won't miss it. But for now, you'll have to take my word for it. When we look at the water molecule and we have an oxygen atom and two hydrogen atoms attached to it, the molecule itself is bent. And there's a concept in chemistry called polarity. The bond is polar based upon how strongly one atom attracts electrons versus the other one in the bond. So when you just look at oxygen and hydrogen, we find that the electrons are more strongly attracted to oxygen, and we use this little arrow with a plus on the end of it. This shows the plus end, this shows the negative end. Now, it's not a complete charge because this is a covalent bond. It's not an ionic bond. So we have to use, rather than use a plus down here, we put a little delta in front of it, which means slight positive charge. And this is a slight negative charge. And then you're going to get one over here. And I guess we want to balance, we'll put a 2 there. That just means that this bond in chemical terms is the bond and the molecule are polar. That is, they have a differential negative positive ends to the molecules. Now that's important for how water behaves with respect to the things that we want to put into it. Okay, so I got a little video here if it'll work. Hope it works. It's not narrated. I think it was made in Canada. That's why it's English and French. This shows the approach of water molecules to a crystal of salt. We have sodium and chloride in your structure, and how the solvation takes place. So notice how the molecules are oriented. The chloride ion is negative, So the positive side of the water molecule is what attaches to the chloride. And then this is sticking out in the open and other water molecules are associating with it. Like that. And they're exerting a force. And the combination of those forces pulls that chloride ion out of the crystal and exposes a fresh surface. Okay. And it just keeps going until one of two things happen. Either all the salt's gone into solution, or the solution is saturated and it can't hold anymore. And we've got, let's see, I think it's next semester we use saturated salt solution for some experiment. But you can saturate a salt solution. You can even saturate a table sugar solution. It takes a lot. It takes a massive amount of table sugar to saturate a solution. But that concept of saturation and having solid in the solution at the same time as you have the solution is used to make rock candy. If you dissolve a lot of sugar in water and you exceed the solubility at room temperature, then you get all of it in solution. Then as it cools down, if you have a string in there or another sugar crystal for it to attach to, then it'll start to grow. And as it gets colder, the solubility decreases and the sugar comes out of solution and attaches to that clump of sugar on your string. Now you got a piece of rock candy. Okay. So when a solution forms, and remember, a homogeneous mixture is a solution. Remember that? Okay. And the solvent in this homogeneous mixture or solution is the major component. And there can only be one solvent. The rest can be as many as you want. Solute. Let's try that again. Solutes are the minor components, and they can be infinite number. However many you want, or how many is available. So in most cases, we'll say aqueous solutions, and we use this suffix. If we put something in solution like sodium chloride, then we'll say aqueous, right, to designate that the solvent is water. In most cases, the solvent will be the major component. That table sugar solution that I was talking about, you can start off with a lot of water and start putting sugar into it. And its solubility is such that you can put more sugar in there than you have water, and it'll still go into solution. But we started off with water as the solvent, so we keep it that way, even though the sugar is now the major component. Okay. Just to avoid confusion. The electrolyte is an operationally defined solute. So if we put a solute in solution and it breaks up into ions, which means now it can conduct electricity. Pure water is an insulator. Low voltage will not flow through water. Now, high voltage is another story. But these electrolytes are defined by their ability to make the solution conduct electricity. So when you get a urinalysis or a blood sample workup and the report comes back to the doctor, it'll have a list of electrolytes in it. Sodium, chloride, calcium, magnesium, phosphate. I left one out. Did I say potassium? Potassium is probably in there. These are electrolytes. in your body fluids, they are ionic. So your blood should conduct electricity. All right. If the addition of the electrolyte to solution conducts a large current very efficiently, then we say it's a strong electrolyte. And these are qualitative definitions. If you don't get a lot of current through the conductor as it passes through the solution, the current passes through the solution only weakly, then that's a weak electrolyte. For example, sodium chloride would be a strong electrolyte. It will conduct electricity very efficiently. Acetic acid, vinegar, right? If you try to pass a current through vinegar, you get some current through it. And if you have a light bulb in the circuit, the strong electrolyte will have a bright light and the weak electrolyte will have a weak light. And then non-electrolytes are those that are not electrolytes. They will dissolve in water, but they will not conduct electricity. And sugar is a good example. It will go into solution, but it won't conduct electricity because it doesn't go into solution as a consequence of being ionic. It goes into solution as a consequence of forming a special type of bond with water that we haven't got to yet. Now, the rule is in this class, stop me if you have a question. Okay. All right, here's a demonstration of electrolytes and non-electrolytes.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
Okay. What just happened is, I guess in psychological terms, is multiple sensory inputs. I gave you all that first, then you saw another way of presenting it, and that's supposed to reinforce it. Let's see if we got any others. No, that's it. All right. So, when we discuss, eventually we're going to talk about stoichiometry of solutions. And in order to do that, we need to know something about the nature of solutions itself. A solution is a mixture. In other words, every component of the solution retains its identity, its chemical identity. There's not a chemical reaction. But sometimes when you put solutions together, you do get a chemical reaction. And it depends on several things that we'll talk about in a minute. We need to know what type of reaction is possible. So that means we need to know what's in this solution, what's in that solution, or any other that we put together, so that when we put them together, we have an idea of how they're going to react with one another. So that's the nature of the reaction that we're talking about. Then we also need to know the concentrations, because usually the reaction will be more vigorous or they'll be faster if the concentrations are increased. You have more probability. The probability is greater for the reactants to interact, to come in contact. So that's where we're headed. So first of all, the concentrations. This is one of the most used expressions for concentration. I don't know if you've ever seen it before, molarity. Right? We talked about the mole. We know what a mole is. Molarity is simply the number of moles of substance in a given volume. And in this case, the volume must be in liters. So it's moles per liter. Okay, that's the definition of molarity. And this, by the way, let me extend this further. This is the volume of the solution after you put the solute in it. Okay. The reason we express it that way is because when you put a solute in the solvent and you are tempted to say, well, the final volume is going to be the volume of the solute plus the volume of the solvent. But it's not always that way. Sometimes it's greater, most often it's less. Because the solute tends to go into the holes, the spaces between the solvent molecules. And that reduces the overall volume. So you can't just add the two volumes together and get the final volume. You have to measure the final volume of the solution in order to do the calculation. So, for example, if we say we put 6 moles of hydrogen chloride, right? Hydrogen chloride would be what? A gas. If we put that many moles of hydrogen chloride in 2 liters of aqueous solution, then we have a 3 molars hydrochloric acid solution, our naming convention. And we would write it aqueous Cl, or you can put the aqueous on the other side. Right. Let's see, let me move this up just a bit. There we go. So suppose we have and by the way, this is an equation. Molarity equals moles divided by volume. It's like any other math equation. If you know or are given 2 of these, you can find out what the third one is. Right? You just solve for one unknown, like any algebraic equation. If we have a 500-gram sample of potassium phosphate, 500-gram sample, can we calculate the molarity in 1.5 liters of solution? Not as given, because that's not moles. That's grams. So how do we get moles out of that? Well, let's work backwards. In order to get moles from grams of a substance, you need to know the molar mass. How many grams per mole? What is its mass per mole of compound? Then you can convert this, use that molar mass to convert it into moles. And then we can plug that in here and put the volume there. So we're given potassium phosphate in English. You can't calculate the molar mass from those words. You have to know the formula. That's why I was so adamant about learning how to write compounds. Because if you don't know how to write the compounds from the name, you can't get there. I mean, you're dead in the water. So potassium, we know, is K, correct? Yep. Phosphate, that's a polyatomic ion, which is PO4 with a 3- charge. That's an alkali metal with a 1 plus charge. So we need 3 of those to make the compound. Right? You don't have to have that there to do the calculation. So what we need is the molar mass of potassium phosphate. So 3 times what? Potassium is 39, rounded to 2 places. 39.10 grams per mole. That's for the potassium. And then the phosphate, we have 1 phosphorus, which is 3097. Right? And we have 4 oxygens, which is 16. So we just add those together. Give a calculator. Right. You will need a calculator if you don't already have one. Okay, good. It's a bona fide calculator, not a cell phone, right? Okay, good. All right. Okay, so 39.1. This thing cranked up. Times 3 is 117.3. Then I'm going to add 30.97 to it. And then what's 4 times 16? 64. Right. So the total is 212.27 grams per mole. Right. Now we have a conversion factor. Right. We've got grams here, but we want moles. So moles has to be in the numerator and grams in the denominator so that it will cancel. And that's 212.27. Go. So I divide 500 by that value. And let's see, I can keep 4 significant figures, right? This is an exact number. This is the one that controls the significant figures. I get 4 of them. So I got 2.356 moles of potassium phosphate. Now we can put it in our formula. The molarity then is 2.356 moles per 1.5 liters, right? 1.50 liters. And now I can only keep 3 significant figures. So 1.57 molar is the concentration of our solution in molarity. There it is. Right there. Okay. Now, if we had been given, say, we know the molarity, and we've got, I don't know, maybe only 1 liter. So if we have 1 liter, and we'll find this, just say 1 times that, we have 1.57 moles. We've only got 1 liter. And then if we want to find out how many grams of potassium phosphate is, we just work backwards, right? We've got this value, moles. We flip this over so that the moles will cancel. That times 1.5 will give us a mass of potassium phosphate. Right? So you can jump on your horse and ride off in every direction. All right, that was the concentration of an ionic compound, the whole compound, moles of that compound. But if any of you are going into the medical profession, any aspect of it, then you'll eventually need to keep track of not molarity of the compound, but molarity of all the components, ions and non-electrolytes as well. Why? Well, for instance, what's the normal saline solution that's isotonic with your tissues? 0.9% sodium chloride is isotonic. So if we convert that to molarity, I forget what it is, but you have a molar value that's isotonic with your cells. And if you're going to infuse, stick an IV in somebody and infuse a solution into them, you don't want it to be hypotonic or hypertonic. It'll damage their cells. So we need to know what's the concentration of the ions as well as the non-electrolytes. See where I'm going with this? Okay. Now, we usually don't give them straight sodium chloride unless they're diabetic, maybe. More often than not, we'll give them something like lactated ringer solution, which is gentler on your system. And then there'll be a port for sticking antibiotics and painkillers and stuff in the flow as it goes into the patient. But that's the carrier. Okay, so how do we do that? Well, if we have 0.25 molar calcium chloride, Right? Is that correct? That's an alkaline earth, 2+ charge. That's a halogen, -1 charge. Yeah. 2 minuses balances a 2+. In solution, this breaks into calcium 2+ plus 2 chloride ions. Right? And calcium chloride is completely soluble. We're going to talk about solubility maybe Tuesday, but take my word for it for now. The calcium chloride is completely soluble, especially at this level. So you're going to get how many moles? What's the molar concentration of calcium ions? If it's 1 mole of this is that molarity, then this should be the same molarity as that, correct? 0.25 molar. How about chloride ions though? For every 0.25 molar calcium chloride, you get twice as much, 0.50 molar chloride ions. Okay? It's a ratio thing. All right, so what would be the total ionic strength of that solution? Well, it'd be this concentration plus that concentration. 0.75 molar ions. Okay. I know that's not on the slide, but I couldn't help myself. All right. So which of the following solution contains the greatest number of ions? Right. Remember, last time we met, I talked Henry Ford. Here's another case for Henry Ford. We've got A, B, C, D. That's it. So A is 400 milliliters of 0.1 molar sodium chloride. 400 milliliters of 0.1 molar sodium chloride. 300 of calcium chloride. And 200 of iron 3 chloride. Oops. Shortchanging myself. Those are all soluble in water. Essentially soluble. And then the last one, 800 milliliters of 0.1. Let's see. Yeah, that's got a 0. 0 molar sucrose. All right, what's the question? Greatest number of ions. We can simplify things for ourselves. Does sucrose make ions in solution? No, it's a non-electrolyte. So we don't even have to do this one. All right, so now we're going to change 400 milliliters into the number of moles of the compound. And then further, we're going to chain together number of moles of compound to number of moles of ions. Okay. So in order to do that, we need this relationship. And if we're going to go moles of ions, that means we have to solve this. We have to solve that for moles. Right? So molarity, that times volume gives you moles. Only that's not in liters. Okay. So I'm going to give you a trick. Just save yourself some trouble. If you multiply molarity times milliliters, you get a unit called millimoles. Okay. So here we have our volume, here we have our molarity, and we should get moles of, well, actually, I was going to chain them together. This is going to give us millimoles of compound. Maybe I'll do them to keep it from getting complicated, right? So you can follow along. Let's do that one. Let's just do them separate calculations. How about that? So 0.1 times 400 is 40. I'm going to keep I know we should round it off to 2, but I'm going to keep all of them just to avoid rounding error in the final answer. So 0.1 times that would be 40.00 millimoles of compound. Okay. So this one is easy, 30 and to 20 millimoles of compound. Okay. Now that we know how many millimoles of compound we got, what's the ratio of compound to number of ions in the compound? That's what we want, because our final answer needs to be the number of ions. So for every mole of compound, how many ions do we have here? 2, a sodium ion and chloride. How about this one? We got a calcium ion and 2 moles of chloride ion. So we have a total of 3. And here we have 4, right? Okay, now we can multiply these out. And that gives us 80 millimoles. Let's see. Now I'm going to restrict to 2 significant figures. Oops. 80 millimoles of ions. And this is 90, right? 90 millimoles. And this is 80 millimoles. Right? So, oh, you want me to prove to you that millimoles is correct? I can do that. Let's say this one is 400 mils times 0.1 gives us 40 millimoles. So if we have 40 millimoles of the compound in what volume? 400 milliliters, right? 400 milliliters. Okay. If we were to calculate molarity, I want to prove to you that this is molarity. So what does milli mean? Milli means 10 to the minus 3, doesn't it? So if we take that milli away and substitute in here 10 to the minus 3, 10 to the minus 3, now we have moles per liter. But if we divide 10 to the minus 3 into 10 to the minus 3, those go out. So we're still dividing 40 by 400. Okay. Just, I wasn't sure if you believe me. I know you're going to take my word for it, but that's not good enough. You might have to explain it to somebody sometime. Okay, now that we know how many millimoles, well, while we're at it, how many moles is that? 80 millimoles. Same thing. Milli is 10 to the minus 3. So 80 times 10 to the minus 3 moles. Or 8 times 10 to the minus 2 moles is the actual in moles rather than millimoles. Okay. But we're just comparing greatest number of ions. That one right there. B. All right. This is more problem solving stuff. What's the question? What do you need to get the answer? Do you have all the information you need? Or do you have to go out and get some more information like periodic table or some of that useful information that's at the back of every review document? Right. Remember, all those pages at the back of the review document will show up again in the test, in the exam. Then gather all your information and then plot out, plot your strategy. How are you going to use that to solve the problem? That's why when I get a word problem, I take the information and suck it out and put it on the board in a way that I can make sense. Right? Because number one rule, word problems are meant to do what?
Trick you.
Huh?
Trick you.
Yeah, they're meant to confuse. Exactly. Yeah. That's the primary purpose of a word problem. They're separating the wheat from the chaff, or they're separating the goat from the sheep. If you really don't understand what's going on, the word problem is going to throw you for a loop. And the best way to handle that is practice, practice, practice. That's why that review document has lots of problems in it. Probably more than you can do in the time allotted. Okay, so the moral of this story, the solution with the greatest number of ions is not necessarily the one with the greatest volume or the formula unit with the most ions. Because iron 3 chloride had more ions in it, but calcium chloride had the greatest number because of the calculation we did. All right. All right, here's a daily skill that I and my companions used to use all the time. Well, that's redundant. Daily skill. I used it all the time. Is dilution. Example. We would work in that. We had a soil testing lab, and they would have soil samples coming in from all over the state. This was in Louisiana. They come in from the county agents and from the farmers, and the soil testing lab had to run various tests on the soils and tell the farmer how to best supplement that soil with either some type of fertilizer or lime, perhaps. And they come in by the hundreds. And the solutions that we prepared were of a specific concentration of each of the solutes. So if we had to make up enough solution to do all those samples every time they came in, we spend all our time making up big vats of the stuff. So what we did was we had the right ratio of each of the components in a more concentrated form, right? 100,000 times more concentrated. And then we just take an aliquot out of the concentrated solution and dilute it. We'd still have the same ratio of all the components. We dilute it to the right volume, and then we could go with our extractions. So this is the basic formula. Sometimes it's written like this: M1V1 equals M2V2, or you could say the molarity of the concentrated solution times the volume that you take out of the concentrated solution, right? That product equals the molarity of the desired diluted solution times the final volume of the diluted solution. Okay. Now let me see. Let me explain that to you. Why does it work? Okay. Notice, based upon this formula, molarity equals N times V. Then if we say M times V, N divided by V, that's equal to the moles. So if we've only got one solute, let's keep it simple. Say we have one solute that's our component A. That's our A solute. And if we multiply its concentration times the volume we take out, that gives us so many moles. So we have moles of A here because of that. Okay. Now, if we take it out of this concentrated, we have A in here. If we take it out of this concentrated one and it goes into a volumetric flask, right? We need a volumetric because it's marked at exactly the right volume. Say it's 1 liter. We'd usually use more. Like we had 5 and 10 liter volumetric flasks that were huge. Anyway, you take your aliquot out of here, a certain volume of the concentrated one, and it's a molar concentration here, we get moles of A, right? So we got moles of A going out. Where does it end up? It ends up in here. Now we have moles of A in here. Okay. Now we dilute that moles of A to 1 liter or whatever volume we want. And that moles of A now is the same on both sides. We took out so many moles here and we put it in here. Right? So if moles equals moles here, and on this side, we know that we're going to have a different concentration, a diluted concentration, because the volume is going to be different. So the moles of A now equals that. So because A equals B and B equals C, then A equals C. So this one equals that one, this one equals that one. That means they're equal to each other. That's why it works. So now that you've got 4 variables in this formula, if you know 3 of them, you can calculate the 4th. And we usually do know the concentrated one. And we usually do know which concentration we want to end up with and how much of it we want, right? We know those. Usually what you're doing is calculating how much of this one do I need to take out and dilute to that volume to give me this concentration. Okay. All right, this is the animated version. Right, the moles transferred is the same. It doesn't change between here and there. Even if you take it out and sit it on the bench and let it evaporate for a while, you're still going to have the same number of moles you put in there. All right. Let's see, concept. A 0.50 molar solution of sodium chloride in an open beaker sits on the lab bench. Which of the following would decrease the concentration of the salt solution? So how would you decrease the concentration of that solution? Let's just think about it. If we have a 0.5 molar sodium chloride solution, how would you decrease the concentration? Can you, you need less sodium chloride per volume, right? So you got 2 choices. Either decrease the amount of sodium chloride in that solution, which is kind of difficult to do, or add more solution, add more volume of the solvent, right? So we put more solvent in there, that decreases the concentration based on the formula. Right? If we make this value bigger, total volume bigger, that decreases this quotient, doesn't it? Yeah. Okay, so add water to the solution? Definitely. Right. Pour some of the solution down the sink? No, because you're pouring some of this down the same way as same time as you're pouring this solvent. Solvent are still in the same proportion. You didn't change anything. Add more sodium chloride, that goes the other direction. Right, you're increasing the concentration. Let solution sit out on the open air for a couple of days. That goes the wrong way too. You're removing solvent because sodium chloride is not volatile, not at these temperatures. At least 2 of the above? No, just that one. Add water. Okay. Now we have a dilution problem here. Let's see if we understand the concept. What's the volume of 2 molar sodium hydroxide solution needed to make a 150 milliliters of 0.8 molar sodium hydroxide solution? So here's where I take the word problem and I say, what are the values? We recognize it as a dilution problem because you're starting with 2 molar sodium hydroxide, you're ending with 0.8 molar. We know that's a dilution problem. So we want concentrated, concentrated, diluted, diluted. So I extract that information from the problem. The concentrated is 2 molar. The volume, minimum volume of that 2 molar is the unknown. We don't know what it is yet. The final volume is going to be 0.8 molar. There we go. And the final volume of the diluted solution is going to be 150 milliliters. Okay. So now we can use our formula. Concentrated. We want to know this one. So let's solve for that. There we go. So the diluted we want is 0.8. 0.8 molar. The volume of the diluted is 150 milliliters. And the concentrated is 2 molar. Go. So, should I have changed that volume to liters? The answer is no. Because this is a ratio. Whatever volume you have on one side, you're going to have the same volume on the other side. Okay. Now, if we use the parent formula, molarity equals moles per unit volume, that does have to be in liters. But this ratio will cancel milliliters, it'll cancel liters, it'll cancel buckets if you want to use that. But whatever unit you use here, you're going to get in your answer. Right? Because that cancels and leaves us with milliliters. That's dimensional analysis. That tells you what the units are going to be over here. All right, so 0.8. 0.8 times 150 divided by 2 is 60. Let's see, we got 3 significant figures here. So this is 60.0 milliliters. That's the volume of the concentrated solution that we need diluted to 150 milliliters to give us 0.8 molar diluted solution. Here we go, animated for your pleasure. Here we go. So we used to do this so much. Just do those calculations in our head. And most of the time, we do the same preparation every day. And so we just memorize what to do. It's like a recipe. All right. Now, types of chemical reactions. We're going to move away from this and talk about types of chemical reactions. Here. Now, these types of chemical reactions, they don't have to be in solution. They can be any phase, unless the description specifies a solution. Otherwise, they could be any phase possible. So we're getting away from solutions for a moment, sort of. Solutions are still there. We're taking the whole universe into account. Major types of solution. I will say this, preface whatever we're going to see here as some of these reaction types can be common, can be included in one reaction. One reaction could be precipitation. It could also be a double displacement or a double replacement. Okay. So these are descriptive terms that sort of help us categorize reactions. Precipitation reaction, what does that mean? A precipitation reaction is one typically where you put two or more solutions together. And remember, solutions you can see through. You can shine a light through them and you don't see the light. You don't see the light. Say I have a beaker here and I shine a light through, you can't see the light in the solution. You could come around here and see the light coming out, but you don't see it in there. That solution, if you put two or more solutions together and you get a solid produced, that's a precipitation reaction. Okay. Acid-base reaction. Second semester, we're going into this in much more detail, acid-base chemistry. But for now, an acid-base is simply you add an acid to a base and they neutralize one another. Okay, that's all there is to it. The consequence of an acid-base is, chemically speaking, a salt. It doesn't have to be sodium chloride. It's salt in chemical terms, plus water. So the salt would be the cation from this reaction plus the anion come together. So for instance, if this is sodium hydroxide is the base, and this is hydrochloric acid on this side, then the anion would be chloride and the cation would be sodium. And they would come together and form that salt. And what's left over? One hydrogen and a hydroxyl makes water. Okay, that's an acid-base reaction. An oxidation reduction reaction, and I think I've got slides on this, but I feel like talking about it first anyway. Oxidation reduction reaction is one in which electrons are transferred during the reaction. So one reactant loses electrons and the other reactant accepts them. Electrons must move for an oxidation reduction reaction. Okay, those are the basic types, major types of reactions. Now we can look at these reactions from a different angle, and we can see a synthesis reaction or a combination reaction is where you have simple, usually an element plus an element yields a more complex. So an element plus an element makes a compound. That's the simplest type of synthesis reaction. Sometimes synthesis reactions can also be a simple compound, a bigger compound. But most often you'll see it as an element plus an element makes a compound. A decomposition is just the other way. Complex makes simple. Okay. Single displacement. Single displacement is, say we have an element here and we have a compound here, and say this is a metal. This is a metal. So this is the cation in the reaction, and this one displaces that one. So now we have B off by itself, and A now is in the compound. That's a single displacement or single replacement. A double replacement would have a compound, CD, and then these would just swap places with one another. Right? So we'd have CB plus AD. That's a double displacement. Okay. And the last one is a combustion reaction. Essential for a combustion reaction is some compound plus oxygen yields products. Okay, always. If it doesn't have oxygen, elemental oxygen, it's not a combustion reaction. So one of the simplest combustion reactions is what sent the space shuttle into space. This starts off as a liquid, but by the time it gets to the rocket engine, it's a gas. And so, and that makes water. And at those temperatures, it's a gas too. So we put two here, and now we're balanced. That's a combustion reaction. Okay. Or when we go in the lab next week to get our bearings, we're going to use a Bunsen burner. And a Bunsen burner is essentially natural gas, which is mostly methane, and combines with oxygen from the air and makes carbon dioxide and water. That's a combustion reaction. We've added oxygen to it and lit it. All right. So there's a precipitation reaction, and it's also it's a type of double displacement reaction that produces a solid. Say one of these is a solid. That would be a precipitation reaction. Here's an example. Barium nitrate and potassium chromate. So you just swap places. The nitrate and the chromate swap places with their partners, and you have barium chromate, which is insoluble, and potassium nitrate, which is still soluble. Right, so you get the barium chromate is your precipitate, it's the solid. Okay. Another example, silver chloride. Put a solution with silver, another solution with chloride, and you mix them together. You get this. Silver nitrate and sodium chloride in this case makes silver chloride is the solid. I think that's slow motion. Yeah, maybe not. This one has silver and thiosulfate ion. Makes a different color, but it's still precipitate. Barium sulfate is insoluble. Anybody ever had a barium enema? That's what they use, barium sulfate, because it's insoluble. Your body won't absorb it, so there's no hazard of toxicity. But barium is a massive atom that attenuates X-rays very efficiently. So that's why they shove that into your colon to take pictures. Okay, copper sulfate and sodium hydroxide. Pretty blue. That's because of the copper. Beautiful chemistry. All right. So, AQ, like before, AQ is used to represent a solution, an aqueous solution. So if the solid dissolves in the solution, aqueous solution, then we say it's soluble. And if it doesn't, we say it's insoluble. That forms the precipitate. For now, we're going to say that slightly soluble is also insoluble. Next semester, we're going to go into the weeds and look at the difference between soluble as an absolute versus insoluble. It's either one or the other now. And for qualitative analysis, that's a useful tool, right? And in your, oh, you guys let me get away with this. We're starting a new section, and I've got a bunch of handouts. Let's see. Anybody need I already gave you lab techniques for next week. Okay. And everybody else got lab techniques Tuesday. Then you need another one there. All right. Let's take time out. Get a copy. Oh, wait a minute. I already did this, didn't I? Tuesday. Well, I'll say this is part of the course. Don't forget what I'm doing, and my students just watch me. It's forgiveness, right? It's like pulling the fish out of the water and watching it flop around in your boat deck. That's your instructor. Okay. So for now, Insoluble is absolute, soluble is absolute. But we will learn next semester that there is this gray area. You can have slightly soluble, and we can actually calculate how much of it is soluble. So that'll come later. Right now, I'm not going to hit you with that. It's too early. Now, these are the solubility rules that we would use qualitatively for doing experiments in the lab where we want to isolate precipitates. Right? You don't have to learn these rules. I just put them there so that you know that they exist. And they're arranged so that if you're looking at a double displacement reaction and you have to say, all right, I've got rule number 4 and rule number 1 are working in this chemical reaction. Which one do I go with? You go with the one that's the smaller number, the one above. So if they satisfy conditions for 1, you can forget about 4. 1 rules. Or if you have 6 and 4, 4 rules. Okay. But the easier way is, excuse me, we'll come back to that. Where is it? Oh, there it is. There's your solubility chart. This is in your review document. Right? It's in useful information. And all you have to do to tell if you've got a soluble salt is to take the cation and match it up with the anion on the left-hand side. The cation's across the top. It's like, well, they don't ever use them anymore. Road maps with those little distance triangles at the bottom, where you say, this is where I am and this is where I'm going, and you just follow where they meet, and it tells you how far it is. Right? It's like that. So you follow where they meet. If it's clear, it's soluble for our purposes. If it's gray, it's insoluble. So if we look at silver, say silver is right here. Can you see it's not easy to see. Silver's right there at the top. If you go down to chloride and match where chloride intersects silver column, then you find a grayed out square. It's insoluble. Right? But silver acetate just above it is soluble. Silver chlorate, perchlorate, silver chlorate, silver nitrate, those are all soluble salts of silver. But everything else in this list is insoluble for silver. And we got the rules down here at the bottom. If you were chemistry majors, you'd have to memorize those rules. Right? Because lots of the lab experiments that you would do as a chemistry major, you go in and you would do isolations where you're conducting these reactions, and you've got to be able to tell which mixture do I need to add to precipitate a given metal out of the solution. But for us, just use the chart. Okay, now let me go back. I skipped ahead a little bit. Let's see. Here we go. Which of the following ions form compounds with lead that are generally soluble in water? You know, I got things out of order. That solubility chart should have been with this or before this. If we go, pull out your review document, so I don't have to flip back and forth. All right, just pull out a copy of the review document, look in the back, and actually on the back page. There's your solubility chart. Okay. You don't have a copy? Better be in there somewhere. Yeah, there you go. Okay. Do you know how to have a copy? Oh, okay. Here. All right. So if we say lead, then all we have to do is go over to the lead, which is way over here next to the last one on the right at the top. And you follow it down and just say, all right, for a sulfide, lead, go down to sulfide, it's insoluble. All right, so that's not it. Lead down to the chloride, it's grayed out, it's insoluble. Lead down to the nitrate, soluble. Okay, so that one's soluble. Sulfate is down here. Here it is, sulfate. Nope, it's grayed out, it's insoluble. And sodium is a trick question. You don't form compounds with a cation and a cation. It's a cation and an anion always. All right, so that E answer is just to throw you a curveball. All right, I think the last thing we're going to talk about in the remaining 6 minutes is writing these double displacement reactions where you have a precipitate form. And this is one of those reactions. I mentioned last time that most of the reactions you're going to be given to balance, you'll be given both the reactants and the products. But in this case, we can deduce what the products will be because we know this is a double displacement reaction. For this example, we have silver nitrate. And if I said, if I told you, write me a balanced equation for silver nitrate and sodium chloride in solution, what's the reaction? You know that silver is a 1+ charge, nitrate is a 1- charge, and it's soluble. We also know that sodium chloride is soluble. So what kind of reaction are you going to have? Double displacement, sodium replaces the silver. So we're going to have sodium nitrate. When you look it up, it's soluble. And you're going to have silver chloride. It's insoluble. There you go. Now, one thing about these types of reactions is, what's the driving force? The driving force is the formation of the solid. Because once you form the solid, you take it out of solution. It's not available anymore. So it's like you suck it away and the reaction just keeps going that way. All right. So this is what's called the molecular equation. Molecular equation. Why? Because it has entire compounds in the reaction. Now, is it balanced already? One silver, one nitrate, one sodium, one chloride, one chloride. It's already balanced. Okay. But if it's not, at this point, you need to balance it using our budget method. Remember, silver, nitrate, because nitrate doesn't change, we can use it as a balancing unit. Silver, nitrate, sodium, chloride, and then tally them up and then do your magic, right? Using those hints that I gave you. And have you looked at chapter 3 video yet? Okay, so you saw me doing all that. Good, okay. I didn't want to stand up here and talk a foreign language to you. Okay, but we know that in solution, we actually have individual ions. In aqueous solution, this will be the complete ionic equation. We separate the ions out. Silver plus in aqueous solution. Nitrate in aqueous solution. Sodium in aqueous solution. And chloride in aqueous solution. That's what's actually there in solution at the time of the reaction. And then what do we have as a product? We have sodium ions. We have nitrate ions. And we have the solid. We have to write it as a unit because it precipitated out. That's the complete ionic equation. All right. The net ionic equation is those ions that are not necessary to form that precipitate. In other words, you're going to find those ions unchanged on both sides of the equation. Right. Sodium is here and here. Cross it out. Chloride is here. Nope, it's in that compound. Nitrate. Nitrate's there. Silver's here. It's in the solid here. Right. So now the net equation is simply silver aqueous plus chloride aqueous yields silver. That's the equation that actually drives the reaction. The other utility of the net ionic equation is that suppose you go in the lab and you want to do this reaction, but you've got silver nitrate, but you don't have sodium chloride. You got potassium chloride. Can you still do the reaction? Yeah. Potassium's just going to be a spectator. These are spectators. They're just sitting around watching things happen. So if you have potassium here instead, right, it's going to stay over here like that. It's just a spectator. You still get the same reaction. Okay, as long as you have the same molar concentration, you get the same result. All right, I think I'm out of time anyway. This is another example. We don't have time to go through it, but this equation says write the balanced equations, formula equation or the molecular equation. You can use either term. Formula equation is probably more correct because these are not molecules. Molecules are entire and they stay intact, like water molecules. No, these are ionic compounds. So formula equation, complete ionic equation, net ionic equation for what? Cobalt-2 chloride. So you have to be able to write cobalt-2 chloride up there and sodium hydroxide and then balance the equation. So that one's balanced. Then we break them apart. Notice that we go from COCl2 here to CO2 plus there and 2 Cl minus because you had 2 in the compound. Right? So now it becomes, that subscript becomes a coefficient. Okay. And we'll pick it up here next Tuesday along with the lab.